Start the recording. Okay, so welcome, my friends. I'm just going to go over what we went over last Wednesday and Monday, because on Friday we just went through the assignment. So last Wednesday we went through regioselectivity and halogenation reactions of alkanes. So if you remember, regioselectivity is when in a chemical reaction there's one product that's more favorably formed over other products. So that's where you get major and minor products. And regioselectivity in halogenation of alkanes is determined by the reactivity of the alkyl radicals that are formed in the intermediate step. So if you remember, a tertiary radical is a radical where the unpaired electron is on a tertiary carbon, is connected to 3 other carbons. So tertiary radicals are more reactive than secondary and primary. Those arrows are supposed to go the other way. My bad. But yeah, you guys know this. So tertiary radical products are more favorable than secondary primary because they're more stable, so they can be formed faster. So that reaction mechanism goes faster and therefore forms more products. Okay, so I have an example here for this reaction. Okay, so does anyone want to take a stab at which one of those would be the major product? Come on, Jacob, take the stab. The one at the very end. Thank you, Jacob. So this one, right, would be the major product. And these would all be minor products. So I'll show the mechanism for that one. I'll stick with black. So your first step in the mechanism for all of these halogenation reactions are your initiation, which is you're going to break up your halogen into your 2 radicals, right? And then your radical is going to attack your hydrogen on your alkane. And from this bond, 1 electron is going to go here. That should be a half arrow, but 1 electron is going to go to this hydrogen to make that hydrogen-chlorine bond, and then 1 of these electrons is going to go back to your carbon to make this radical. And we're going to form HCl. And then your next step, you have your alkyl radical, which is a tertiary radical, right? Because this, I want the color, okay. This carbon is a tertiary carbon, right? It's connected to 1, 2, 3 other carbons. Okay. So we have our alkyl radical, our tertiary radical, and then we're going to take another molecule of our chlorine, and this radical is going to attack 1 of these chlorines, and then this bond is going to break, and one of the electrons is going to go back to this chlorine radical, or to the chlorine, to reform that chlorine radical. And then the other one is going to go here to make this carbon-chlorine bond. So we have our product here, and then our byproduct here. Okay? We feel good? Okay. So, and we can show the mechanism for one of the other products just so you can see the difference. So again, our first step is we break our chlorine-chlorine bond. to make our two radicals. And then our radical is going to attack a different hydrogen. So, I don't know, let's say this one maybe. We're going to attack this, and then this bond is going to break, and one of these electrons is going to go to this bond between chlorine and hydrogen, and then the other one is going to go back to that carbon to make a radical. Okay. So this is a primary radical. It's not very favorable at all. So this is going to be a very, very minor product because you have the option to make a tertiary radical. So this one is not very favorable, but we will still show. And then we have HCl. So now we have our alkyl radical. It's going to attack another molecule of our chlorine. So we're going to attack this, and then this bond is going to break. One electron is going to go to that chlorine, and the other one is going to go here to make that carbon-chlorine bond. So there's our product, and there's our byproduct. And like I said, this is a very, oh goodness, this is a very minor product because it's formed from a primary radical. Does that make sense? Okay. So after that, we started section 2, which is alkenes and their reactions. So an alkene is just an organic compound that has one or more CC double bonds. And the general formula for those is the same as cycloalkanes, which is CnH2n. Okay, so carbons with a double bond are sp2 hybridized instead of sp3. So they're no longer tetrahedral, but carbons with a double bond are trigonal planar instead of tetrahedral, which has a bond angle of 120 degrees instead of 109.5, like your tetrahedral carbons. So I have the bonding structure shown down here. Let me get my pointer. So I have my two carbons, and each carbon has 3 sp2 hybridized orbitals, as you can see here, and has 1 unhybridized p orbital. Okay, so for a double bond, this sigma bond is formed by the overlap of this carbon's sp2 orbital and this carbon's sp2 orbital, which forms a sigma bond because this is a hat-to-hat overlap, right? And up here, we also have this attraction here, which forms a pi bond, which is just 2p to 2p. Okay, so those sigma bond and the pi bond together form a double bond. Does that make sense? Okay. So this shows the hybridization in alkenes. So if we remember carbon, just regular in ground state, we have 2 electrons and 2 s, and then this is supposed to say 2px, 2py, 2pz, and then we have 2 electrons in the p orbital. So when we excite it, this electron is bumped up to 2p. So we have 1 electron in 2s, 2px, 2py, and 2pz. Okay, so after hybridization, we form 3 sp2 hybridized orbitals. And we also have 1 unhybridized 2p orbital, which is where we form our pi bond. Okay, any questions so far? Okay, so, and the last thing I want to talk about, I didn't have a ton to talk about today since we went over the assignment last Friday, so we didn't have a ton of material, but the last thing was cis-trans isomerism in alkenes. So because of the pi bond, alkenes cannot rotate freely around a CC bond like alkanes can. Because sigma bonds you can rotate, but because of the pi bond, you can't rotate that molecule without breaking that bond, which normal conditions don't have enough energy to break that pi bond. Okay, so this causes cis-trans isomerism or geometric isomerism. So cis, if you remember, means the two same groups are on the same side of the double bond. And trans just means they're on different sides. So as you see it on here, this is the same example we used in class a bunch of times. It's 2-butene. So we can either have cis or trans. And this one's cis because we have the methyl groups on the same side. And this is trans because they're on the different side. That's about it. Everyone good on that? Okay. And that's all I had, really, since we didn't go over too much. Does anyone have any questions about anything, even if it's like from today or from lab, anything like that?
For the cis-trans bonds, for the cis one, does it just have to be symmetrical? Like, could the two carbon hydrogens there be on the left together be cis? The two H's on the other side?
Wait, sorry, what?
Does it just have to be like symmetrical? Like, is that what makes it?
Okay, so to have cis-trans isomerism, these two groups on the carbon have to be the same. Okay, so like these have to be the same or these have to be the same. But like if this was a different group, then you'd have to use easy configuration. But because we have two methyl groups and two hydrogens, then we can say cis or trans.
So if that sounded like a kindergartner, it's like the wings of a butterfly, it has to be the same?
Yes. yeah. If you want to think of it like that, then it works for me. Any other questions? Anyone online? Hi, Dr. Sun.
Hi, Lydia.
Hello. How are you?
I'm good. I'm good.
Glad.
You did well.
Thank you. I didn't have a lot. Yeah.
No, I know.
Okay. Yeah, I can send it out, Kaylin. Okay. If nobody else has any questions, then that's all I got. You're welcome. Also remember, I'm a tutor. I do have tutoring hours open for this class. If you guys feel like you want more one-on-one help. And if you don't want to make an appointment, you can always email me and ask me questions or come to me after class. I'm always here to help.